Hi guys, welcome back to the channel. In this video we are going to discuss about parallel adder, or we can also call it as ripple carry adder. This concept is fell under combinational circuits, so let's get started. This is the full adder circuit diagram. You can see that is known as block diagram also simply. So down is the actual circuit diagram for the full adder. For this parallel adder or ripple carry adder, the full adder is very most important. So if you want the full video of the full adder, I am giving the video in the description, check it out. So in this, the two XOR gates, two AND gates, one OR gate is very must for the formation of full adder. I hope you know full adder. Let's get see the other things further. As I mentioned, this is the block diagram of the full adder. In this we are seeing that two inputs, mainly A and B. So one is carry, that is C in, that is before carry, and we are getting two outputs, that is sum and carry out. So we can observe three inputs and two outputs. Parallel adder or ripple carry adder means the cascading of full adders is known as the parallel adder. So if you observe there, this is known as 4-bit parallel adder or ripple carry adder, because if you observe we have four full adders we can observe. That is, the inputs are first one A1 B1 A2 B2 A3 B3 A4 B4. So you can also observe each full adder as input. The first, if you observe the first full adder FA1, that is C0 A1 B1, the outputs are two outputs, that is S0 C1. If you observe the second one, that is inputs are A2 B2 C1, outputs are S1 C2. Likewise, if you see the last one FA4, the inputs are C3 B4 A4, the outputs are S3 C4. I hope you can understanding. That is three inputs and two outputs. But we have to cascade like in a parallel way, that is known as parallel adder or ripple carry adder, in a continuous fashion. Then you might now get a question that why we need the parallel adder or ripple carry adder, because if this is the basic thing, the name itself suggests it's an adder. It will add the binary digits. So if you observe, we have 4-bit binary decimal or binary number. We have the second one, that is in the form of B, that is also 4-bit binary digit. We are going to add both of them. So for that we are going to use the 4-bit parallel adder. With the help of full adder, we can add only 3 bits at a time. That is the 3-bit. Not at a time 3-bitted binary, not at a time 4-bitted binary digit. It can add only 3 binary digits, not at a time, like this. So for this representation or for this addition, we are going to use the parallel adder or the cascading things of the the full adders. From the addition also you can observe. So that is the blue highlighted in blue box, that is 1 1. The output is 0 and carry is 1. So that is can be performed with the half adder. So next one, or full adder also we can perform with carry 0. So if we observe the second one, that is 1 1 0, is performed with the help of full adder. The next one also 1 1 0 full adder. Next one also full 1 1 0, that is full adder. So with this, all these things you can observe. There are mainly four columns. 4 columns means we can simply say that is as a 4-bit parallel adder. And final carry that we are getting is the 1, that is I am dragging down, that is final output 1, and that is the output as 1 1 0 0. And if you want sum of two 8-digit binary numbers, then you can use 8-bit parallel adder or 8-bit carry ripple adder. So after adding that, you are going to get 8 sum terms, and if you might, according to the question, if carry presents, then carry also will come as output. So now let's see the 8-bit parallel adder, the circuit diagram. So if you observe the first 4 things that we have already saw in the 4-bit parallel adder. So again I am going to add another 4-bit parallel adder. I am going to merge the C4 with the last carry of the thing, so that I can get the sum terms from S0 to S7, that is 8 sum terms. So that is 8 output terms that we are getting, and the final carry we are getting from C8, that is the final carry that we are getting as output. We did nothing, just we cascaded 4-bit parallel adders. And the next thing is 16-bit parallel adder. So take a look over this. So I have cascaded two 8-bit parallel adders, that then it becomes the 16-bit parallel adder. So nowadays in computers we are using 32-bit parallel adder or 64-bit we are using. So that's the main thing. In future it might be updated. So many chips are included in the transistors, and including more are increasing day by day. So they might increase the bit level. But as now this, so this is the 16-bit block diagram that we can say of the parallel adder or ripple carry adder. The main thing that we have to understand the first one, that is 4-bit parallel adder, so that we can understand all this, we can apply wherever we want. So let's understand clearly, so what is meant by propagation delay, how the carry is moving, how we are getting the sum as output. So let's see all these things in the 4-bit parallel adder. Main thing we should know that if you want anything, we have to take some example so that we can understand very clearly. If you observe, this is the example that I have explained already. So this example only we will be going to apply in the block diagram of 4-bit parallel adder, and we are going to verify our outputs also. So let's see the first one, that is 1 1. So we are going to pass 1 1 as A and B in the first full adder, and carry as 0 because we do not have any carry beforehand. So after passing, we are going to get output as 0 because 1 plus 1 is 0, and carry would be 1. So next column is, that is 1 1 0. So first one is carry, second is A, that is 0 is B. So we are going to pass that. So if you see, carry is 1 and A is 1. So 1 plus 1 is 2. 2 means 1 0. So output is 0, carry is 1. That is C2 here. If you see the next column, that is 1 1 0, that is 1 is carry, 1 is A, 1 0 is B. So we are going to pass in the third full adder, that is 1 plus 1 again, that is 2. 2 is 1 0. So 0 is our output, 1 is our carry, that is C3. Last and final most full adder in 4-bit parallel adder is that is 1 1 0. So we are going to pass that 1 1, and we already have the carry, that is 1. So after passing that is 3. 1 plus 1 plus 1 is 3. So 3 means the sum is 1 and carry is 1. So if you observe that, we have to take carry also. So 1 1 0 0, that is our final output. You can cross verify from the normal binary addition, and in the passing of full adders also you can cross verify, both are same. Now let's understand what is meant by parallel adder and ripple carry adder with some definition. So let's see the definition of parallel adder. So a digital circuit that adds two binary numbers in parallel. In this meaning, each bit position is added simultaneously. So this is the meaning that we have already see the addition, that is parallel addition. So at a time, all these B1 A1 B2 A2 A3 B3 B4 A4 will be added at a time. So and produces some S1 S0 that will be produced. So this is known as parallel adder. That is the reason it will add at a time parallelly, or the inputs are, we can say, inputs are passed at a time parallelly. So then why it is gave name as the ripple carry adder? Because a type of parallel adder where this carry signal propagates to the adder in a chain from at least least significant bit to most significant bit. So this is the important point also, because we are passing from least significant bit to MSB. So the propagation delay is known as ripple carry adder. So you can observe there. So just we have started with C0. Then after some delay, so it will not pass directly, because see the second addition, that is B2 A2 C1. For the C1 it has to wait the full adder 2, so it takes some delay. So this delay is known as propagation delay. So this will be explained in this video only, for let's wait for that. So propagation is very late in some of the late applications and late procedures, but propagation delay is very important to be known, to be understand. In exams like GATE and many more competitive exams or college exams may contains this term called propagation delay. This is the very important term that we need to know. So if you see the block diagram of the full adder, so this is the block diagram. So in the block level, I am repeating, in the block level of the full adder, we are going to consider, that is TS and TC. TS means the propagation delay of the sum. So the outputs are two only. The first one is sum, second one is carry. So the propagation delay of sum is the propagation delay of sum, TS, and TC means the propagation delay of carry. So we have only two outputs. So we are going to represent two propagation delays for sum and carry. For an example, let's take that TS is equals to 15 nanoseconds and TC is equals to 15 nanoseconds. This means, so for the producing the first output, means first sum, we are going to require 15 nanoseconds, or we for the producing the first carry, we are going to require 15 nanoseconds. So apply same things for the whole circuit. We are going to have all carries and all sums at a time. So if you observe, after 15 nanoseconds the second carry means the first carry. So in the full adder 2 we are going to have 30 nanoseconds, because Already we have spent 15 nanoseconds there, and we need to take another 15 nanoseconds, so 30 nanoseconds total. So for the carry 2 also, that is added 15 nanoseconds, because TC is 15 nanoseconds. So likewise, so 30 is added with another 15, so 45. So 45 is added with another 15, that is 60 nanoseconds total final output of sum. So total final output of carry is also 60 nanoseconds. And if you observe, that is 60 nanoseconds, that we can represent as 3 TC plus TS, means 3 times 15, 45 plus TS, that is 15, that is 60 only, that we are going to have TS. So when n for n bit, so sum is equals to n minus 1 TC plus TS. So for next carry, for the final carry, we are going to have 4 TC, that is 4 times 15, that is 60 only. So the total propagation delay for the carry. So if you observe for the carry, that is NTC. You have to note down a point here, that is these formulas for sum and carry is not specially for, this is for just this question only, not for all general purpose. For this question only, according to the question, we have to formulate the output. Or in some competitive exams, they might directly ask the final output expression in terms of TC and TS. So that is the reason I am saying for a special question. Every question has its own things. So take some examples. Suppose you are using some gadgets like mobile phones. So if you got late by 10 seconds, you might be frustrated. If you got late by 1 hour, so how much you feel? So it's very frustrating, right? So if the inside hardware makes some delays for the incoming inputs and producing the final output in the mobile screen, so it might frustrate the user experience. So for that purpose, we are going to avoid the propagation delay, because if the propagation delay is more, so that gadgets will work as slow as they're possible. So we need to avoid the propagation delay. So how we can avoid the propagation delay in parallel adder and ripple carry adder? So we cannot avoid directly in this type of ripple carry adders or parallel adders. So we can have another type of circuit. In the circuit, we can avoid the propagation delays. That is known as carry look ahead adder. So we are going to see this type of circuits in the upcoming video. So stay tuned. Remember, without having any propagation delay, this adder will work. As I before mentioned twice, that is at the block level. As already said, that is at the block level. But inside the block, we have some logical circuit, right? So logical circuit is this. We already know full adder, full circuit is this only. So inside we have some 5 gates, that is XOR gates, AND gate and OR gate. So each has their individual propagation delays. So we don't know that. According to the question, we have to follow all these rules and things. In the question paper, they will mention the XOR gate, the propagation delay is this, the AND gate propagation delay is this, like that they will mention. But for some example, we are going to take the propagation delay of XOR gate is T XOR, and the propagation gate of means propagation delay of AND gate and OR gate will be same. We are assuming like that. It's not same. We are assuming in this situation, that is as TP. So this is the example that we have to follow, very much important this example is. So follow this example up to last. So they have given the propagation delay of XOR gate, that is 20 nanoseconds, and the propagation delay of AND gates and OR gate, that is 10 nanoseconds. So we have to form a ripple carry adder, and we have to formulate all the sum and carries the propagation delays. So let's find it out. So as this is the single full adder, so we are having 4 single full adders by cascading each other. So let's observe the first full adder. So this is the circuit diagram of the first full adder. In that we are going to have these things. So you can observe, first we are going to obtain the full adder's propagation delay of the carry. The propagation delay of carry. So if you observe the carry, so how it is obtaining, you can first have to pass with the XOR gate, then AND gate and the OR gate. So this is the way we are going to pass to get the final output of carry. So for that, in the passing way TC1, we are going to have the OR gate plus TP. So this gives T XOR plus 2TP. So this is the important formula, you have to remember this thing. And we can put the values and check it out, that is 14 nanoseconds. That is given in that question. Next thing we are going to do in this is to find the propagation delay of the sum. So for the sum, we are going to have the S naught. For that we have first have to pass the first XOR gate and the second XOR gate. So for that we are going to have the TS1 as T XOR plus T XOR, that is 2 times T XOR. So we are going to have the final output as 40 nanoseconds by putting the values in that expression. If you observe clean observation in the two expressions, that is the TC1 and TS1. So the TCE1 is T XOR plus 2 TP and TS1 is 2 times T XOR. So this is for the first full adder. So in the same way we are going to have all the full adders output expressions of T means the propagation delay of carry and the sum. So let's see that. So this is the thing that we are going to have the 4-bit parallel adder. So in the same fashion, so the first S0 we are obtained that 2 times T XOR. So we have obtained the carry for the first full adder, that is T XOR plus 2 TP. Up to now we have discussed or obtained that only from the circuit diagram. So the next thing we are going to see is that the propagation delays of the S1 and C2, that is the propagation delay of sum and carry of C2. So let's see that. If you observe it clearly, so in the sum, that is B2 and A2, we are going to have XOR gate of A2 XOR B2. We will be going to have some output expression. So the output expression will be again XORed with the C1. So that is the thing, that is the main motto of the XOR gate, that is B2 XOR A2 XOR C1. So we already saw in the full adder. So the propagation delay of the sum is how we can obtain. That is we can obtain. So we have the propagation delay of the previous carry, that is T XOR plus 2 TP. So we have to add that with the T XOR because we have already completed the XOR operation of B2 XOR A2. So we need to just add the XOR operation, that is T XOR plus the previous carry, that is T XOR plus 2 TP. So that gives our propagation delay of TS1. And if you observe the propagation delay of the carry, that is TC2, so that you are going to obtain, that is T XOR plus 4 TP. You are going to add the extra 2 gates after the first output. In the same fashion we are going to fill out all these things, that is the propagation delay of TS2 and propagation delay of TC3, that is the propagation delay of the sum of S2, that is T XOR plus 4 TP, because the propagation delay of the carry of TC2, that is T XOR plus 4 TP. So the XOR operation of B3 XOR A3 will be waiting for the carry. So we need to add the carry. So after adding carry, we need to add the previous XOR gate, that is T XOR. So I hope you are understanding this. So basically sum means we are going to have 2 XOR gates cascaded. So 2 XOR gates cascaded means, so first XOR gate is the XOR, that is B3 XOR A3, that is added after second, that is second term. So the first term is the previous carry. So that is the thing. So we should add these both delays so that we are going to have the sum delay, that is TS2. So we can also get the TC3, that is the propagation delay of carry, that is T XOR plus 6 TP. From this, in the question, if they ask any of the value, you can find that with the help of the given expression also only. So they have given already T XOR is equals to 20 nanoseconds, TP is equals to 10 nanoseconds. According to the expressions, you can find any carry, any the sum expressions propagation delays. So in the question paper they might ask give the propagation delay at the second half adder, or give, that is sum or carry. So or give the propagation delay of the sum, that is in the full adder 4, like that they can ask. You can put the values and you can find the output. Again I am saying these output expressions are only for this circuit diagram according to the question that they have mentioned, that is T XOR is equals to 20 nanoseconds and TP is equals to 10 nanoseconds. If they change these values, you are going to have another things. This is the basic thing that you should all know, how to use the full adder, 4-bit parallel adder or ripple carry adder, what is meant by propagation delay, how it works in the 4-bit parallel adder. I hope you understood all these things. Thanks for watching up to now.